Hi, welcome to a new lecture. Today is an introduction to autoencoders. So we'll be trying to understand the intuition behind autoencoder, and also we will code an autoencoder completely from scratch. So there are two purposes to me recording this video. One is with an intention to keep this as a standalone video. So even if you are watching this lecture without any context, you will understand most of the important aspects about autoencoder if you are interested in the concept behind autoencoder. But I'm also planning to keep this lecture as part of an ongoing series called Transformers for Vision, in which the next topic that we are planning to cover is transformers for generative models, like using transformer for generating images like stable diffusion. But before going into stable diffusion, we need to talk a little bit about diffusion models. Before talking about diffusion models, we need to talk a little bit about variational autoencoders. And before talking about variational autoencoders, we have to talk about autoencoders. So that is the second context in which I am creating this lecture. Either way, if you have followed the Transformers for Vision at all, or you are watching this video as a completely separate lecture video, both of that will work for you. You will enjoy the lecture and you will at the end of the day understand what exactly is this famous architecture, what are its uses, what are the challenges of the vanilla autoencoder architecture, and how can you code one from scratch to sort of create your own images. This is not the greatest of generative AI models, and I think many people know that, but I think the exercise of constructing an autoencoder from scratch will give you a great intuition about latent space, about some ideas behind probability, etc. So let's get into the lecture. The basic architecture of autoencoder looks like this. There is an encoder, there is a decoder, and in between there is something called as the latent space. So whenever you see this kind of trapezoid shape with width decreasing, you can imagine that to be a representation of compression going on. You will see this even in convolution operation when your spatial dimension is shrinking. So in encoder, the information that you provide at the input, the information can be an image of certain number of pixels. That information will get compressed to be represented in a lower dimensional space. And this space is called as latent space. And decoder, what it does is, it tries to reconstruct the input that you have provided here. So if the input is an image, decoder will try to reconstruct the input just by looking at this compressed version of the same input. So the compressed version of the input lives in this latent space, which is a much more lower dimensional space. And with that, decoder will try to perform reconstruction. Let's try to understand this with a concrete example. So if we consider the MNIST handwritten image as the input, the data is the image itself. And this image, when we are passing it into an encoder, this image by default has 28 by 28 pixels. It's black and white. So you can consider the input data, which is this image, to be living in a 28 by 28, which is 784 dimensional space. How do you get 784? Those are every single individual pixel. So each pixel value you can consider to be residing along one separate dimension. An encoder, what it does is, we can look at the detailed architecture of the encoder in a little bit, but in short, what it does is, it compresses this 784 dimensional data into, let's say, 64 dimensional data. So of course, there will be some losses happening during compression. So when you are inputting this image is taking 784 dimensions to represent it fully. But when you are compressing it to 64 dimensional space, some information, hopefully some useless information, is discarded, and some useful information, which is the most critical for reconstructing the image, is retained in this latent space. And when you perform reconstruction, you are again trying to reconstruct back a 784 dimensional version of the input image. But this time, when you are doing it, you don't have access to the input image. You are only accessing the 64 dimensional latent space. So this is a great tool, right? If you can train such a network, this is essentially a neural network. If you can train it, it acts as a very good compression engine. And how do you train this? You train it by constructing a very simple kind of loss. What is the loss? Loss is basically how bad your reconstruction is compared to your input data. The easiest way to compare this is just do a mean squared error MSE, where mean squared error equal to 1 divided by 784. You have 784 pixels. And let's say the input data is PI data. So this is the ith pixel from the input data minus pixel value from the input data. P reconstruction or PI reconstruction so this is the difference in pixel value between data and reconstruction. You square it and you sum it over I, where I runs from 1 to 784. So you perform a pixel-wise comparison between data and reconstruction, and that is the mean squared error. If this mean squared error can be minimized, it means your reconstruction will look very similar to your input data. What happens if the mean squared error is 0? It means every pixel is perfectly matching. Every pixel in the reconstruction is perfectly matching with the data. This is the idea behind autoencoder. Now, if you have a trained autoencoder, you can just take the encoder part of it. You can ignore the decoder. So if you ignore this part, your encoder part of it will act as a very nice compression engine. It can perform very efficient compression of your 784 dimensional input into 64 dimensions. This 64 is not a fixed number, by the way. We can define whatever, and in today's coding, we will try to pick 64, 12, 2 dimensions, 1 dimension, 3 dimension. We can try all of those. So if you just consider the trained encoder from a trained autoencoder, that encoder part will act as a very nice compression engine. And the trained decoder will be good at converting your compressed version of the data into reconstructed version. Of course, there are some challenges here. We will discuss that soon. So the compressed space will basically look like a n-dimensional space where there will be vectors, right? So this data you can consider as a vector. So originally it is 28 by 28. If you flatten it, it will look like a 784 dimensional vector, which will have something like this, one column where the dimension is 784 multiplied by 1, right? And each dimension will be the value of each pixel. And when you reach the latent representation, the lower dimensional space can be something like 64 by 1, right? So this diagram is just showing the compressed latent space. And this latent space is where all your input data will reside after being encoded. So now there is a challenge. Let's say I want to now generate a new image. If you were to consider autoencoder as an image generation model, you can sample a random point from your latent space, right? And you can hope that if the decoder is a trained model, if the decoder part of the autoencoder is trained, if you pick a random point from your latent space, that point can be decoded or reconstructed into an image. So in this case, you are hoping that the sample data point from your latent space, when you are passing it through decoder, it can be reconstructed into one of the MNIST type of images, right? That's what your hope is. But actually it doesn't happen. If you sample from the latent space randomly, what in reality happens is a messy reconstruction. The reason for this is that autoencoder is learning to represent every single image into one single point in the latent space. So even if you are sampling from the same latent space, the sample data point may not correspond to any meaningful image. So when you are trying to reconstruct an image using your sampled data point, using a trained decoder, you may end up getting a messy image like this, which does not look anything like a MNIST image. One solution to this, which you may think, is how about this? How about we take a reference point and we sample near the reference point? What is a reference point? A reference point is something like this. I input a data. So let's say input data is this handwritten digit 5. And this is a trained encoder, okay? So I use the trained encoder to convert my data point into this. So this is in the latent space. So this is, I'm just drawing it in 2 dimensions because that is the best I can do. But imagine that latent space can be 2 or 3 or any number of dimensions. So this is the latent space. And in this latent space, now we know that this data point directly corresponds to this image. So if we were to pick this data point, we might get a very closely looking reconstruction similar to this digit 5, because we have trained the autoencoder on this data set. So then our thought is, okay, but then what if we pick a point which is very nearby this reference? So what if we pick this green point? So green point is a new point in our latent space, which is very close to this reference point. So the red point is reference point. Why am I calling it as a reference point? Because that point was constructed directly from an input image. Input image was passed through a trained encoder to produce that point in the latent space. We sample a point very close to that reference point, and then we might hope that this reference point, because it's so close to the sample point is so close to the reference point, hopefully if we pass it through a trained decoder, it may construct an image which may look like this handwritten digit 5, right? That is what we are hoping. But in autoencoder, that does not happen. In autoencoder, even if the sample point is very close to a reference, it results in a messy image reconstruction. There are many reasons for this. We can actually do some experiments today in the code. But the main reason for this is that autoencoder actually is mapping an image into one single point. So if I have a handwritten digit of 5, it is being mapped into this point. If I had a handwritten digit of, let's say, 6, or another type of handwritten 5, like this, if I had an image that looks like this, maybe it will get encoded into a point in the latent space that looks like this. Now, there is no guarantee that something in between. So this is handwritten digit 5. This is handwritten digit 5. But there is no guarantee that a point in between might also be a latent representation of a handwritten digit 5. There is no guarantee like that. So if you sample any point randomly, or even if you sample a point close to a reference point, it does not necessarily mean that decoder can convert it or reconstruct it into a meaningful image. This is the reason why variational autoencoder was introduced, but in this specific video, I'm not going to cover variational autoencoder. I'm planning to cover it in a separate video. But today, let's focus on what autoencoder can do and what it cannot do. And if we were to train it from scratch, what does the architecture look like? So these are the things which we are going to do. So I have created a diagram here, which I want to, to have you make a quick walkthrough through this diagram. So this diagram is showing the sort of the architecture of autoencoder that we are going to build today. Some details are missing, but I'll show you another version of the diagram with more details. So you have an input image, which is 784 pixels. So you are in the first step flattening the image. So 28 by 28 is flattened into 784. Then of course there will be activation function, which I am not showing here. Then this 784 dimensional representation will be compressed into 256 dimensional representation, and 256 dimensional representation will be further compressed into whatever is the latent dimension. And this will be a variable. We can define the latent dimension as 64 or whatever. In fact, this 256 is also our choice. We can pick whatever number we want in this hidden dimension. So this is the input dimension. This is the hidden dimension. And this is the latent representation or latent dimension. And then once we have the latent dimension or latent embedding, we again expand it back, use through a hidden dimension of 256. We expand it back into 784 dimensions. And this we can kind of plot like this. And of course, there are activation functions in between. Now, what we are going to do is today we are going to run the code, first write the code and then run the code with latent dimension 1, latent dimension 2. We can also run for latent dimension 3 and higher dimensions. And we can try to construct the images corresponding to originals. So these are the original images 8, 1, 8, 3. And when you reconstruct, we can see what can be done. So here the number of epochs which I ran for is just 5. But we can see if we run more number of epochs, whether our reconstruction look better. Here you can see that if the latent dimension is just 1, every image is getting represented by one number, right? It's just a one-dimensional parameter. Then of course the reconstruction is not very good. And as you go from 1 to 2 to 3, the reconstruction is becoming better, but although it's a bit blurry or messy. See, here 9 is getting reconstructed into something confusing. You can't say whether it's a 9 or 3 or 5, right? This reconstruction. And here what I'm plotting is the latent space itself. Because 1D latent space has only one dimensions, we can easily plot it. So you can see that there is some grouping. Different digits are grouped in a histogram to different latent values. So a digit like this one, a digit 1 is being represented using a latent value whose average is close to 0.5 or something. A digit like what is this pink color? Pink is 6. A digit like 6 is represented using a latent value whose average seems to be like 2.7 or something like that. And if it's a 2D latent space, we can directly plot as a scatter plot in 2 dimensions. And you can see that there are very nice clusters emerging basically. So this is one cluster where all the data points corresponding to digit 0 is living. These red clusters are those data points corresponding to 3 and so on. In 3D space also such clusters emerge, but it will have 3 dimensions to spread. And in more dimensional latent space, we cannot directly plot, but we could do something like principal component analysis to boil the plot of the latent space into 2 dimensions or 1 dimensions, and we can still plot it. So this is what we are going to do. And the architecture that we will use is something which I showed you above, but the only thing which I did not explain is the activation function. So we will have a ReLU activation function, and these are all fully connected nodes, by the way. So if there are 784 nodes here, after each node there will be ReLU activation, and they will be fully connected to the 256 nodes in this layer. I could not draw that many connections, so I just skipped drawing it, but just, all the layers are fully connected to each other. I mean, all the consecutive layers. And then after this 256 node hidden layer, you will have ReLU activation after every node, and then you connect to the latent dimension. Again, it's fully connected. So latent dimension has 64 or 32 or variable number of dimensions, and then back. So this is the encoder, and the decoder basically constructs back from latent dimension something to 256, and then there will be ReLU activation. Following that, you project to 784 dimension, and following that there is sigmoid activation, and then you have the final reconstructed image. And the loss will be mean squared error loss, MSE, which will compare pixel by pixel between the input image and reconstructed image. So this is in a nutshell what we are going to code. And now we can directly go ahead and try to construct this autoencoder in Python. So you can open a Google Colab notebook. This is going to be relatively easy code. So coding autoencoder from scratch. And runtime, you can connect to any available runtime that you have. I have a Google Colab Pro subscription, so I can connect to V6 TPU. But you can also connect to whichever GPU or CPU or TPU, because the code is not that complex. So it probably would not matter too much which runtime you're using. So first, we are going to import libraries that are needed. So first is import torch, which is PyTorch. Import torch.nn as nn. We will need this for inheriting certain properties when we are defining our neural network. So from nn.module, we will inherit certain properties for our class that we will write. Then import torch.optim as optim. And from torch vision, import datasets. So this is for getting MNIST or fashion MNIST. So fashion MNIST dataset, you might know. This is the dataset. There are different classes of these clothings, and you can try to reconstruct these images also. So we can try both MNIST as well as fashion MNIST in today's coding, and transforms for performing transformations on the input image. Then from torch.utils.data, import data loader for loading data into different batches, and from import matplotlib.pyplot as plt. So, and I have imported NumPy also here as per Gemini's suggestion, but I don't think we really need NumPy. We'll see if we need it, we can import it later. Let me delete it for now. This matplotlib is for plotting the generated images. So these are the only libraries. So once this is done, you can just run this. Next is defining the device. So device equal to torch.device. This is standard. Okay. If CUDA is available, use it. Otherwise use CPU. So I just accepted Gemini's suggestion here. So I'm just going ahead with it. Next is the data loading. Data into train and val. So first we can define a variable for batch size. So batch size is the number of images per batch. We can keep it 64 or 128 or anything that we wish. I'll keep it 128 for now, and change it later if needed. Then the transformation that we need to apply, transforms dot compose, compose with C capital. And the only data transformation that we are doing here is to convert the Python image library format data into tensor format. We need tensor format image to be fed into the neural network. So transforms dot to tensor. That's the only transformation. We are not necessarily scaling it based on mean or standard deviation. We can do it, but right now we don't have to do it. Then train underscore dataset. Anyway, we are planning to reconstruct the original image, right? So it's not a multi-class classification problem or anything. So train dataset equal to datasets. So this is where we define whether we want to use MNIST or fashion MNIST. We can start with MNIST, MNIST and root equal to /data. Then this is the folder in which data will be downloaded to. Then train equal to true. Then transform equal to, we can just paste it. So just to avoid confusion, I can just write this as data underscore transform, and then I can pass that here. Otherwise, if I use the word transform, the variable name transform, you may get confused. So transform equal to data underscore transform, download equal to true. Then this is for train dataset. Now for validation dataset, actually there is no validation that we need to do here. We just need to see if the trained autoencoder is creating good enough images. So we don't have to necessarily do validation here. So we can just say train loader. This is the data loader part. Train loader equal to data loader, where we have to mention the data set is the train data set. This is where the data points are coming from. What should be the batch size? Batch underscore size is equal to, so here again to remove confusion, I'll just put this in capital letters, batch underscore size. So we are passing that variable here, and shuffle equal to true. We can just shuffle the batch data. And that's it. So we now have the data set in batches of size 128. And each individual data point will be a tensor. It won't look like an image. It will be in a tensor format, loaded using data loader into this variable train loader. And once this is done, you can just run this piece of code. So now data is being downloaded and train loader is ready. Now we have to write the class that defines autoencoder. So class autoencoder, and into this we pass nn.module so that autoencoder can inherit bunch of properties written inside nn.module. This is the standard argument that is passed into any class which we build in Python if we want to use the predefined libraries in PyTorch, where various properties of gradient descent, etc. are defined for neural networks. Then we say define underscore init. This is the init constructor for initializing the current object. And into the init constructor, we may have to pass a few arguments, but self is the only argument that we need to pass by default. The rest of the arguments we'll figure out if we need to pass or not. Then, so this is the init constructor for the current object corresponding to autoencoder class. But there is such an init constructor in our parent class also, which is in nn.module. So then we say super. Super means we are now referring to the init constructor in the parent class, super dot underscore init underscore. So this will initialize the init constructor in the parent class also. Then we first define the encoder part. Then we have to define the decoder part. And then we have to define the forward pass. So then we can say define forward and here self comma x, where x is the input. So we have to write that encoder, we have to write the decoder, so that irrespective of which loop of forward pass we are in, that is the encoder we are using and that's the decoder we are using. And then in forward pass we do we pass the variable from one layer to the next. So first let's write encoder. Encoder is first the input image comes, so self dot encoder equal to, and this encoder is bunch of layers, right? So you can use nn dot sequential to connect those layers. So what is the first layer? In the first layer you have a fully connected network, so it's a linear connection going from 784 dimensions to, let's say, 256 dimensions. So 256 is now the hidden dimension, and following this there is a ReLU activation. Following this, the hidden dimension is projected into our latent dimension. This is where I can define a variable called latent underscore dim, and I can pass it here. So self comma latent dim equal to, let's say, 32 or something. So the latent space has a dimensionality of 32. And then again, after that, nn dot ReLU. So after projecting into latent dimension, we apply ReLU activation. Then I don't think in the figure I showed this explicitly. Just let me. So after projecting from 784 to 256, there is a ReLU activation. So this part is actually wrong. My bad. I have drawn this ReLU in the wrong place. After projecting from 784 to 256, you have a ReLU. After projecting from 256 to 64 or whatever the latent dimension is, there is another ReLU over here. Okay. So please note, in this image, we don't need a ReLU activation here because there has been no operation. So the only operation happened so far is flatten. So after flattened, vector that is 784 dimension, after it is projected into 256, only then we need the activation. So this is technically not needed, but we will need an activation right after projecting into latent dimension. So two ReLUs, one ReLU after 256 dimension hidden layer, another ReLU after projecting into latent dimension. So this is the first ReLU, this is the second ReLU. That's it. So that is the encoder. Very simple, right? And decoder is self.decoder equal to, again, nn dot sequential. This part is easy. You can already guess what we are going to do. Nn dot linear. And here the projection is from latent dimension to 256 dimensions. And then after that, there is a ReLU activation. And from 256 dimensions, we project again using fully connected layers into 784 dimensions. And after that, we apply sigmoid activation. So that's it. The decoder, that's it. Here, one thing we could do is we can say hidden dimension also is a variable. So hidden underscore dim equal to 256. And then use this variable here. Instead of 256, use the hidden dimension variable. That way, we don't have to keep changing. If I want to change the hidden dimension, I just need to change it in one place. So that also you can do. So that's the encoder and decoder, fairly straightforward. Now we can just define the forward pass. In forward pass, we first have x getting converted into latent. So latent is z. So z equal to self dot encoder, which we have defined above, of x. So x is the incoming input and we are encoding it. And then reconstructed is x reconstructed or x recon is equal to self dot decoder of z. So that is the reconstructed image. And now we can just return the reconstructed image. It will not be in an image format yet. It will be like a 784 dimensional vector, but we can plot it as an image using matplotlib. So we are now returning the reconstructed image. Okay. The pixels correspond, 784 pixels corresponding to reconstructed image. That's it. Autoencoder part is done. As I promised you, this is a fairly easy thing to code. I just ran it to make sure there is no syntax issue or anything. So far, so good. Now we can just write, define the model. So defining the model loss. So auto or model equal to this class name autoencoder. So we are just initializing autoencoder class into this model object. Then criterion equal to, so this is again one of the other places where we use the nn which we had imported. So nn dot msc loss, which is mean squared error loss. So we are not defining mean squared error from scratch. It's not needed. It's already predefined in nn. Then we say optimizer equal to Adam. So optim dot Adam, and the parameters that we want to optimize are the parameters in our model. So model dot parameters, and learning rate also we can define learning rate equal to, let's say 10 to the power of -3, 1e minus 3. This also will be another variable which we can change, and then I just run this block of code. So training loop has not started yet. That starts now. So we can say epochs equal to 5. So just running this for 5 epochs, and model dot train. And so model is set to train mode, not in eval mode. Then we say for epoch in range of epochs. So for loop for running the 5 epochs. Total loss, this is just to keep track of the loss. We initialize it as 0. Then we say for x comma dash in train underscore loader. So from the train loader, we are taking data sets one by one, batches one by one. Now for this batch, what do we have to do? X equal to x dot view -1 comma 784 dot to device. So can you guess why this step is done in this case? So here what is being done is the x is a variable corresponding to our batches. So if batch size is 128, our size will look something like this. You have a grayscale image, so 128 is the batch size, comma 1, comma 28, comma 28, right? This is how the data input will look like. But then you can't pass this. When you are passing this, you want to convert this 28 by 28 by 1 into one single, one single 784 dimensional vector. So what you can do is you can sort of convert this into a format where this remains as 128 and this will become 28 by 28, which is 784. So the view function in Python, what it does is when you say -1, it will automatically calculate what the dimension over there should be. So then you could have asked, why not explicitly mention 128, 784? Like I could have just explicitly said 128, 784, right? Why did I not say that? Why did I say -1, 784? The reason for that is, although we have mentioned the batch size to be 128, all the batches will be 128 except probably the last batch. Because if in my input data set there are, let's say 6,400 images, right? Let's say my batch size is, or let's say I have 6,399 images, okay? And let's say my batch size was 64. Then I will have 100 batches, right? So 100 multiplied by 64 is 6,400. In all the batches, I will have all the first 99 batches, I'll have 64 images. But in the last batch, there will be only 63 images. So we are not sure, although we mentioned the batch size, we are not sure if in every single batch there will be that many number of images or not. Sometimes the number of images in the last batch will be less depending on the total images available in the training data. So if in one of the batches, if this was like 126, then if I explicitly write it as 128, that's a problem. That's the reason why I keep it -1, so that Python will automatically calculate what the dimensionality here should be. Now this is what we can pass into our fully connected layers in nn.linear. So x.view of -1, 748. Actually, this is not 748, right? This is 784. -1, 784, dot to device. Then we say optimizer dot 0 grad. Again, what is this optimizer for 0 grad step? It simply says for each batch, start with 0 gradient, and the previous gradients accumulated will not be considered. And then x reconstructed, x underscore recon equal to model of x. So model was autoencoder over here, model equal to autoencoder, and this class is ultimately returning x reconstructed. So you can say x reconstructed equal to whatever you get out of this model object belonging to autoencoder class. And then loss is equal to criterion, which we had defined. So criterion, and into this we pass our reconstructed image and the input x. Then we say loss dot backward. So we backward propagate based on the loss, and then we take in the Adam optimizer, we move ahead one step, and then the total loss underscore loss equal to total loss plus loss due to current iteration. And we can also define an average loss. Average underscore loss is equal to total underscore loss divided by length of train loader, which is the total number of batches. So this is the loss that is being accumulated batch after batch. At the starting it was 0, but as we move ahead through batches in this for loop, this total loss will keep on increasing. But if you want to know the batch wise average loss, the total loss need to be divided by the total number of batches. Total number of batches you can get from this train loader, length of the train loader. And then we just say print epoch. Then we need to mention the epoch number. So epoch plus 1. So epoch start from 0, I think. So 0th epoch I want to call as epoch number 1. And so 1 out of whatever is the total number of epochs. So total number of epochs is just epochs. So this will print like epoch 1 out of 2, 1 out of 5, 2 out of 5, etc. This epoch is the current epoch over here. Print this and comma loss. And for loss, we can print the average loss. So average loss, and we mentioned the floating point precision. And that's it, I think. I don't think we need to write anything in the training part. Now we can just run this. Let's see if there is any syntax error or something. Okay, mat1 and mat2 shapes cannot be multiplied. That is because hidden dimension 256. Let me just run this once more just to see if the error is reproduced. 128 multiplied by 256 and 784 multiplied by 32. Okay, latent dimension is mentioned to be 32. So we go from 784 to hidden dimension, then hidden dimension to latent dimension. So this is a mistake. So this should be hidden dimension to latent dimension. That is the encoder. In the decoder, you go from latent dimension to hidden dimension and hidden dimension to final dimension. So now let's try run all again. Yeah, now it seems to be working. Let's see if the loss is coming down. So loss, please note, it's a mean squared error loss, which is kind of interpretable. If mean squared error loss is 0, it means your reconstruction is exactly same. So the mean squared error after 5 epochs actually took only less than a minute to run. It's only like 0.01 after 5 epochs. We can run for more epochs if the reconstruction is really bad. So now we can set the model in evaluation mode, model.eval with torch.nograd. So we are not calculating gradients now. X comma dash equal to next of iter of train loader. So we are loading the data set from the training data itself just to see how the reconstruction looks like. And here actually we are just displaying the image that results from the decoder output. Okay, decoder has already trained, it has already been trained. So we are not doing any extra training or any work here. This is just for visualization, just for us humans to see. X equal to x dot view of -1 comma 784. This we had already done earlier in the earlier training loop, but here also we are doing the same. Then x underscore reconstruction is equal to model of x. So here we are just calling the model once again, but model is not set in training mode, it's set in evaluation mode, just to get the final output from the model, the 784 dimensional output. Then x equal to x dot CPU. This is just to set the variable x into CPU device. I think this step we can try skipping, it may throw an error, but we'll see. Then number of images that we want to display. Let's say it is 8 images that I want to display, n equal to 8. Then I can say plt.figure and fig size equal to 12,3. And then we can take images one by one. So for I in a range of n, so we have to plot these 8 images. plt.subplot 2, n, I plus 1. Then plt.imshow. This is where we display the actual image, x of I. So ith image from our input. So we have selected bunch of inputs from our, the batch. Then dot view. So we are viewing it as a 28 pixel image, and color map cmap equal to gray. Then plt dot axis off. We don't need to see the axis here. And then corresponding to this, we also have to plot the prediction. So plt dot subplot of 2, n, I plus 1 plus n. So in matplotlib, 2 means there are 2 rows, 1 row for the original images, 2nd row for the reconstructed images, and there are n columns, and there will be total 8 columns, right? And I plus 1 is the index of the image, and I runs from 0 to 7. So I plus 1 will start from 1. It will go all the way till 8. So we will start by plotting in the column number 1, and a row will go from 1 to 8. And the reason why here the index is I plus 1 plus n is for the index I plus 1. So this is one entire plot. Okay, inside this loop, it's one entire plot. But inside this plot, we are creating subplots. And I plus 1 means it's the index of the actual image. I plus 1 plus n will be I plus 1 plus 8 will be the index of the corresponding reconstructed image. When I plot this, you will understand what this will look like. So plot.imshow x reconstructed, not x, just x recon of I dot view of 28 comma 28 and gray color map equal to gray. And again plt.axis off. And then we just need to say plt.show to display the plot. So let's run this to see what the output looks like. I think rest of the things are already ready. So, okay, now this is the output. So these 8 images, so totally there are 8 plus 8, 16 images that are being plotted. But within each, we are creating 2 subplots. So I will go from 1 to 8, but within each we are creating 2 subplots. So subplot number 1 in the first iteration is this 9. Subplot number 2 is this 9. The first one is the original image. Second one is the reconstructed image. This is the original image. This is the reconstructed image. And you can see that for some images, it's very confusing. So here 5 is reconstructed as a confusing 5 or 6. It's hard to say. And wherever there are some extra features like this, those extra features are not getting reconstructed, probably because you have a lot of inputs of images like this corresponding to 3. And if you really want the reconstructed image to be an exact match of the input, probably you'll have to train for more number of loops and maybe increase the latent dimension size. Right now it is 64. Now one more thing we can do is model dot eval. So we need to plot some things corresponding to every single dimension, right? So I have written a code here, which I don't think I have to write from scratch. This is just meant for plotting. So I'm having a model.eval so that all these latent variables I can store, all the values of the latent dimensions corresponding to every single input image I can store in a variable. And then I can plot like a nice scatter plot, which looks like this, right? So that's what we are going to do now. But this code is a little bit long. It's because I deliberately kept it with few conditions. So one condition was, if it's a one-dimensional latent space, I just want a histogram. If it's a 2D latent space, I need a 2D scatter plot. If it's a 3D latent space, I need a 3D rotatable scatter plot. If it's a higher dimensional space above 3 dimensions, I will convert it into a 2-dimensional space using principal component analysis. I'll find the two most important principal components, which can be easily done using library, and then I can plot it. I'm not going to go into the details of how principal component analysis works, but basically it will find the most important two axes through which the data shows the maximum variance. So this also I'm going to copy and paste here. Okay. So now in the 64 dimensional space, obviously we cannot directly plot. We have to convert it into principal components. So I'm just running the model once more in evaluation mode. And once it is done, I will show you the 2D principal component analysis PCA plot, how it looks like, how the 10 classes of the MNIST data will be distributed, etc. We can also run this once on fashion MNIST. But let's first run this on pure MNIST, just the handwritten digits. Okay, so this is now how my PCA principal component, two principal component axes looks like in 3D. You can see that there is very nice clustering happening. The 10 classes are clustered into almost distinct 10 clusters. Now let's start with one thing. Let's start with the embedding the latent dimension to be 1. What does this mean? If latent dimension is 1, it simply means you are representing the entire image in the latent dimension with just one dimension, with just one number. So of course it will be not so very good, because now with just one number you have to reconstruct your input image. And of course, this should result in a lot of losses, right? So let's run this and see what kind of output we are getting. So now for the same number of epochs, the loss is 0.05 after 5 epochs. Earlier it was 0.01 or something. And these are my reconstructions. Clearly 0 is getting confused between 8 and 0. Same for 2. So most of these reconstructed images look almost the same. The variety is missing. And that is rightly so, because you are trying to reconstruct with just one latent, hidden variable. The distribution will be like a histogram. This is how it looks like. There is a lot of overlap. The digits that are not overlapping so much is 1 has a mean over here, and this blue is 0. So if you are trying to reconstruct 0 and 1, I hope the reconstruction will be good one. So let's see the reconstruction of 0. This is a 0. It is getting reconstructed like this. This is 0. It's getting reconstructed like this. But 1 is not getting. Let's run this one more time, so that hoping that, yeah, see, this is 1. 1 is getting reconstructed almost like this. So 1 and 0, there is good distinction between 1 and 0. Now let's look at the graph to see which data points the distinction is very less. I think the distinction between green and this blue, which is green is 2 and the light blue is 9. Distinction between 2 and 9 is very less. Here they are both occupying the same latent value, roughly around 2.5 or something. So if we are trying to reconstruct 2 or 9, or even this purple color is 4, 2, 4, 9, the reconstruction of those three numbers should not look very different. They might look alike. So 2, 4 and 9, let's see. So this is 2 looks like this, 9 looks like this. Okay, there seems to be difference. 4 is, there is no 4 here. We can run this one more time randomly. See, okay, 2 and 4 are there. See,
The reconstruction of 2 and 4 looks exactly the same, very much the same. And 9 is not there here. Let me run this once more to see if 2, 4 and 9 I can get in one single. Here again I have a 9 and a 2. Look at this, the reconstruction of 9 and 2. So these are all 9s, 9, 9, 9, 2, 9. So these reconstructions of 2 and 9s are all looking the same. I'm sure there are more numbers whose histogram is falling such that the latent value, mean latent value is close to each other. So all these numbers actually have mean latent value that are very close to each other, except 1 and 0. So 1 and 0 are at two extremes, but all the other digits may look kind of similar. So this is with a 1D latent space. What if we change it to 2D? Can we have a lesser loss? So right now just take a look at the loss for same number of epochs, 0.05. If I use a 2D latent space, what can my loss become after 5 epochs? Let's come back after these epochs are done. So this is with 2D, the loss has reduced to 0.046, which is slightly lower than the previous case. And the reconstruction seemed to be marginally better. It's hard to say whether it is incredibly better. It's marginally better for sure. And when we run this again and again, you see the reconstruction is kind of resembling. There is a lot of variety in reconstruction, first of all, and they are resembling the original image, right? Let's look at the scatter plot, 2D scatter plot. Seems like, yeah, I have to run this once. Actually, I should run both of this. I need to first get the latents here stored, and then I have to run the plot once. So this is the 2D scatter plot, and you can see that there is a huge difference between plots of, let's say, digit 0 and digit 1. So this is 1 and this is 0. They are farthest apart. So their plots will have good distinction, but there is a lot of overlap between some of the other digits. But in general, you can see a lot of clusters are there, right? Which means that in the latent space, the regions that you are occupying are kind of distinct. One more thing that I can do here is, in this plot, I'm not sure if we are only plotting positive numbers. I think we are only plotting positive numbers, which is why there is an abrupt cut here. But I'm not 100% sure if we are also converting to negative numbers in the latent space. We are applying a sigmoid at the end, which is between 0 and 1. So I don't think we can expect to have negative numbers at the output. Okay, so makes sense. So this is for two-dimensional latent space. We already saw the 64-dimensional latent space. Now what we are going to see is looking at the 3D latent space. So 3D hopefully will be even better. So here the loss was 0.046. For 1D space it was 0.05. For 64D it was 0.01. For 3D hopefully it will be somewhere in between. So for 3D, the execution is done, and I don't think the loss significantly reduced. It's 0.041, lesser than before. And reconstructions are, again, slightly more better, but I cannot say that for sure. Like looking at these 8 images, I can't say for sure reconstructions of all images are really good. It's okay. And here is the 3D space, latent space. You can see that again there are clusters, but since it's in 3D, it's hard to say which ones are overlapping, because in the third dimension maybe the overlap is less, but this is how it looks like. The best thing we can do is increase the number of dimensions in the latent space to, let's say, something like 128. So let's keep this as 128 and let's see how good the reconstruction is. I will also do one thing, which is in epochs I can increase to 20 to see the best reconstruction. And then let's pick a random latent vector which is not connected to any reference image, a random latent vector, and see how the reconstruction looks like. Okay, so I'm going to run this 20 epochs. So the execution is finished and the loss is very small, 0.003. And when you look at the reconstruction, they look almost same as the original. So the top row is the original, bottom row is the reconstruction, really good. We can also plot the principal component, 2 principal component axis. That is what you're seeing here. There are clusters. You can see some overlap, but looking at the quality of reconstruction, which you can run again and again, can assume that, the space is large enough to provide enough variability for any kind of input image. But now here is the other interesting thing to do. If we randomly pick a latent vector from the latent space, will that vector also result in a good reconstruction? As we discussed earlier in the theory part, it probably does not, right? So here is a random latent vector. So here what we are doing is we are picking a random vector from the latent space and then passing it through decoder and using that decoder output to display the resulting image. Okay, so this I can run any number of times and look at the sort of images resulting from my 128 dimensional latent space if I am randomly sampling vectors from the latent space. These are utter useless images, right? They are complete random looking reconstructions. This is the number one issue with autoencoder if you are using it as a image generation model. It is not at all a good image generation model. It is good to reconstruct the image provided the latent vector resulted from an actual input image. On the other hand, if you are creating a random vector whose dimensionality is in the latent dimension, latent space, the resulting generated output image, which is from the model decoder, will look something like this. So you can run this any number of times in the hope that if the latent vector is close to one of the vectors corresponding to an actual reference image, you may get a good, resulting reconstruction. But you can run this again and again. It's very difficult to get a very good reconstruction. So this is the problem with autoencoder, and this was one of the primary reasons why variational autoencoder was introduced. We'll discuss about variational autoencoder in a separate video, but I hope you understand the value of autoencoder as a really nice compression mechanism. If you have a trained autoencoder, the encoder part of the autoencoder alone can be used for constructing good compressed versions of your input data. And decoder as such, if you are just using decoder part of the autoencoder, it is not that useful because the reconstruction has meaning only if the input that goes into the decoder is corresponding to some actual image. But if the input which goes into the decoder is a random data point from your latent space, your reconstruction will have no meaning. But your encoder alone, a trained autoencoder, you can use just to take apart the encoder, and that encoder can be used to encode whatever new images you have to input. So if it's an MNIST image, you can use that to be input as an input into the encoder to produce a very good compression in the latent space. Now, before we wind up, one last thing we can do is do the same for fashion MNIST. So here we say fashion MNIST, and number of epochs we can reduce actually. Let's keep it 5. And let's not have, I don't want to see the latent space or anything. So let's just comment out this part of the code. This is just to see how good the reconstruction look like, right? So just 5 epochs, 128 dimensional space. This also we could reduce to 32 or something like this, just so that the code runs a little bit faster. And oh, there is some error, fashion MNIST. I think fashion MNIST is also 28 by 28 MNIST data set pixels. Yeah, so this is also 28 by 28, exactly like MNIST, but except these are these clothing apparels. There are these 10 classes, t-shirt, trouser, all these, and different varieties of that. So now let's see. So if you remember the loss for 64 dimensions, right now we have defined the actually this is 32. For 64 dimensions, the loss was 0.01 after 5 epochs. Here also it's almost reducing it to that level. And hopefully the reconstruction will look very good. Let's see in a minute. So the execution has finished, and this is the reconstruction. So shoe, some full sleeve shirt, sneakers, all of it's getting reconstructed in a very nice way, but a lot of details are missing. So this shirt actually has this looks like a female upper body wear, and it looks like a there are stripes, but those stripes are not getting reconstructed. And if I run just this block once again, it will reconstruct and construct another set of these clothing apparels. So you can see that it's blurry, but reconstruction is working just like MNIST. So I recommend you to play with the parameters, basically the latent dimension, try one-dimensional data, also try a larger number of dimensions and see how the reconstruction looks like. And just feel free to comment what was your results from your experiments. So thank you so much. That's a good place and time to wind up today's lecture. I hope you understand autoencoder, how it works and for what it can be used and for what it cannot be used, and why do we say that it's not a great generative AI model, because the reconstruction is not the greatest. In next lecture, we will discuss about variational autoencoder, which is significantly better than autoencoder at generalizing the latent space representation capability. So at that time, you will understand why aspects of probability and Gaussian distribution has to be introduced into the latent space, because right now, even if you pick a representative point right next to, even if you pick a point right next to a representative reference point, the construction, which is the reconstructed image, is very bad, but that need not be the case. If you are representing your latent space as a probability distribution, you can sample from nearby your mean and still end up getting a really good reconstruction. So we will discuss all of that in the variational autoencoder lecture. So take care until then. Thank you so much. See you soon. Bye. Back to a new lecture. Today we'll be discussing about variational autoencoders, or VAE. So the context of taking up this topic at this point of this course is twofold. One is as a standalone architecture, VAE is very important. So even as somebody who has nothing to do with vision or multimodal large language models, VAE as a separate topic in itself, it's very significant for you to understand. It teaches you a lot of things. Second thing is, if you want to understand deep generative models like stable diffusion or even the diffusion model, which was originally proposed before stable diffusion, it's very important that you understand variational autoencoders in the first place. So today's lecture, I have divided into two parts. First, we will try to understand the architecture of variational autoencoder and what it does. And in the second part, we will be coding a VAE from scratch. Coding wise, in my opinion, today's lecture will be relatively easy for you because you have already coded much more complex things as part of the Transformers for Vision series. So today's coding will be relatively straightforward, but we can do a little bit of experimentation with the model itself to see what are some different outputs that results from our different, let's say, hyperparameters or latent space dimension, etc. So we'll discuss all of that. So first thing is, I had posted a video about autoencoder. So I recommend you to have a look at it. But in any case, I will give you a quick recap on autoencoder, which is easy to understand. So autoencoder has this following architecture. It's fairly straightforward. It has an encoder, it has a decoder. And what the encoder does is, if you have a data like an input image, encoder will compress it into a space called as the latent space. So latent space has number of dimensions, which is much less than the original number of dimensions in your input data. So if you had a 28 by 28 image, you will have around 784 pixels, right? And each of these pixels you can consider as one dimension. So overall, here the data is residing in a 784 dimensional space. But the latent space will have a much smaller number of dimensions. It can be 10, it can be 64, whatever. But the number will be much smaller than your input embedding dimension. And the purpose of this latent space is to sort of represent the same information which is contained in your input data in a much more compressed format. And how do we know if this compression is valid? To know if this is valid, the only thing you need to do is try to decompress it. So using the 64 or 10-dimensional representation of your data in the latent space, use a decoder to reconstruct your original image. If your reconstruction looks very close to your input data, it means your latent space is able to represent your input in a much more compressed fashion. So this is the basic idea behind autoencoder. Now, how does the encoder and decoder look like in terms of architecture? It will be a bunch of neurons in a fully connected neural network. So usually, if you have an input image of 28 by 28 pixels, you will convert this into a layer of flattened pixels. So this will be 784. And then the flattened layer will be projected into, let's say, 256 dimensions. And you can project this 256 dimension after some ReLU activation. So let me draw activation like this. After this, you can project it to, let's say, 64 dimensions. And this will be your latent space. And then after each layer, you will have ReLU activation. Then project it back to 256. Then project it again back into your original dimensionality space. So this part you will call as encoder. This middle part you will call as latent space. The second half you will call as decoder. This same architecture you have seen in many instances. If you remember, or if you are familiar with UNet architecture, you will see such an encoder-decoder architecture. If you remember how spatially our images were getting shrunk in a convolution operation, it has a lot of similarities with what the encoder does. So the latent representation is nothing but a vector, basically using a vector to represent your entire image. So if this vector has 16 dimensions, you will say your latent space is a 16-dimensional space. All right. So you're hoping that with this encoder, you are able to compress whatever information is there in 28 by 28 pixels into just 16 numbers. So you're going from 784 numbers to 16 numbers. This autoencoder, however, has some problems. We will discuss that in today's lecture before going into variational autoencoder. So first thing is latent space is very compact and lower dimensional, which means a higher dimensional, bigger data you can compress into a smaller data, right? That is the advantage of latent space. But this is what is happening in a autoencoder. Let's say I pick a point from my latent space. So now this is the smaller dimensional space. I pick a point from the latent space, and let's say this point resulted from my encoder. So I encoded some image into this point. Then I'm picking that point and I'm trying to decode it using a trained decoder. Okay, so here I'm only considering the decoder part of my autoencoder. So if this point resulted from a trained encoder, then I can reconstruct an image with fairly good clarity or accuracy. And this reconstructed image will look very similar to a input image. So if my input images are from MNIST, the reconstructed image will also look like an MNIST image. But the problem is that latent space in an autoencoder is very disorganized and irregular. So there is a very specific reason why this term is used. So the reason is if you are sampling from a random point in the latent space. So let's say this latent space, you pick a random point, either this point or this point. So it's a random vector. And now you are trying to decode from this vector the original image, meaning you are trying to reconstruct the original image using this vector, which is a random vector in your latent space. Then what typically results is a messy reconstruction. You will almost never get the original image back, or you will almost never get an image which resembles the MNIST image. It will look like a meaningless image. I will show you an example in the code itself. Now, one might think, okay, I can resolve this issue by making sure that I am sampling from nearby a reference point, right? So what I mean by that is I take my trained encoder. This is trained encoder. This is my input data. My input data using the encoder is converted into an encoded reference point. So let's say this red point is my reference point. So this red point basically is the encoded form of this image of the letter 5. Now I will say, now the sample point which I am picking from my latent space is this green point, which is very close to my encoded reference point. In your opinion, do you think this will result in a very good, high quality reconstruction? Or do you think this will still result in a messy reconstruction?
So here what we are doing is we take an image which we know is a good image. We are passing it through an encoder, and through the encoder we are producing the encoded version of this input image, and then very close to that we are taking a reference point. That reference point, do you think will it result in a good good meaningful image? And here is one more question. Okay, let's say this red point is the embedding of digit, let's say 3 or something like that, or digit 5 itself. And let's say this point is the embedding of maybe digit 8. Okay. Now, if I pick a point between these 2 points, let's say I pick this point. So this point is exactly in the middle of the reference point for 5 and reference point for 8. By just normal human logic, we may expect this point to be something that is a mix of 5 and 8, right? Or it may be closer to 5 or closer to 8, or a mix of those two. A mix of 5 and 8 can be, let's say, a 6. Because, if you add one extra thing here, it is 6. If you add one more thing here, it resembles 8. So maybe you might think, okay, maybe it might look like a 6. But what actually happens is, it doesn't matter in the latent space. If you are having an autoencoder, in the latent space, even if you pick a point that is very close to a reference point, you will still get an image that is meaningless. You will get some gibberish. The reason for that is, in the autoencoder, you are doing some hard training. So by hard training, I mean this data point, you are saying that this data point, which is this image of 5, which actually can have a lot of variance, right? 5, I can write 5 like this, a bit slanted, a bit like this. All of these are maybe 5s. So if ideally I were to construct a latent space, I would say this point represents 5, and I have a distribution around this point such that irrespective of whether I pick something from here or from here or from here in the latent space, all of them should be equivalent to different variants of 5, right? So ideally, according to human logic, any version of 5, slanted or thick, or anybody's handwritten digit of 5 is a variant of a mean tendency. A mean 5 can be something with no slant and average thickness. Then variance can be something with higher thickness, lower thickness, more slanted, or whatever. Those are all variants of the 5 around a mean. But here, we are not even considering the fact that there can be a variance. What we are simply doing is we are hard coding this digit 5 into a latent space, and we are trying to reconstruct, and we are trying to train this model. Let's also discuss about how exactly would you train. If you want to train a reconstruction like this, what kind of loss would you provide? How would you penalize the autoencoder in this case? For making poor reconstructions, how do you penalize the autoencoder? What is the loss function? The loss function can simply be mean squared error, right? You compare the reconstruction with the original image pixel to pixel, and mean squared error would simply be 1 by n sigma I equal to 1 to n yi cap, where yi cap is the reconstructed pixel value for ith pixel, minus yi, which is the original pixel value for ith pixel, square. And when do you think this mean squared error will be minimum? Mean squared error will be minimum when the reconstruction is as close to the data as possible, right? So you are forcing this data point to be represented with a very specific latent point, such that that very specific latent point, when you reconstruct, results in an image that is very close to your input image. You are not allowing the latent space to kind of explore different possibilities. You are making, through mean squared error, you are enforcing your latent space to fixate one latent variable corresponding to one input image. And because of that reason, the term irregular is used, is because if the latent space was regular and organized, then it would look something like this, or it may look something like this. It would have been, let's say it's a 2D latent space. I might be able to say something like all the points in this region of the space belong to digit 5. All the points in this region of the space belong to, in general, digit 3. Something in between will look like neither digit 5 nor digit 3, something in between. So this is called as organized and regular latent space. But disorganized or irregular latent space would not have these properties. For that, there is no guarantee that if this is correct, if this is the latent variable corresponding to digit 5, there is no guarantee that if you pick something just close to that, there is no guarantee that this will also resemble the vector corresponding to digit 5. It may be completely random. The concept and problem. Okay, understood the concept and problem with normal autoencoder, but why would I pick a random point from the latent space? Great question. So originally, when autoencoder was introduced, people also had the thought that, oh, can I use a decoder now to produce, in generative AI, you want to produce or generate images, right? So if you want to generate an image, would you pick, can you, randomly generate a latent space point? And can you use that point to generate a completely new image? So that, can you consider autoencoder to be a deep generative model? And what is deep generative model? A deep learning model which has the capabilities to generate, in this case, generating image. That's the reason why you might want to pick a random latent space point and hope that that random latent space point may correspond to a completely new image of a handwritten digit of 5 or handwritten digit of 7. But in autoencoder, it is not strictly a deep generative model, because when you are trying to reconstruct an image, you will never be able to reconstruct a completely new looking image, because the moment you pick a random point from the latent space, you will end up with a messy image reconstruction. You have to be very, very close to or extremely similar to the reference point to generate a meaningful image. So the autoencoder is a really good model which can be used for compression. If you want to compress the data and store it, it's really good for that. But if you look at the decoder individually, even if it's a trained decoder, this is useless, because it can only be used for reconstructing the actual reference point. It can never be used for image reconstruction for a completely new or completely random latent space point. But this is where the idea of variational autoencoder was introduced. Can we somehow organize our latent space such that different regions in the latent space may mean something? That was the idea. I'll show you one code for autoencoder first, and then I will show you the construction of variational autoencoder. So this is the code for autoencoder. It's very simple. I'll go through variational autoencoder, and this is just a subset of that. So once you understand variational autoencoder will be very easy. So this is for fashion MNIST dataset. I'll simply run the code. But what happens here is you are embedding your fashion MNIST images, which are basically images of, I think, 10 classes of different fashion wares, into a 32-dimensional or whatever the latent dimension is, into that space. And then you will try to reconstruct those same input images using autoencoder. So let me show you one example once this code is executed. So don't worry about not understanding the code right now. I am going to show you how to construct this not this code, for a slightly more complex version, because variational autoencoder has few more complexities. Okay, so for my first question is, in autoencoder, this 0.03 is mean squared error, okay? And can you just try to think about what does 0.03 mean? Mean of square of error between pixel values. So if pixel values are in the range 0 to 1, 0 and 1, 0 means black, 1 means white. Yes, I will also share this notebook. Yeah, okay, my execution is done. But this top row, you see 2 rows here.
The top row are the original images of different, upper body wares. Bottom row are the reconstructed versions of the same image. So I encoded it and then decoded it. How does the encoder look like? It's a neural network. I'll show you that when we are when we are discussing the variational autoencoder architecture, I'll show you that. It's fairly easy. But look at the difference between top row and bottom row. Top row is the original images. Bottom row is the reconstructed images. Reconstructed images are a little bit blurry, but still we can make it less blurry by maybe running for more epochs and maybe increasing the latent space dimension to slightly higher. Right now it's 32. Maybe we can increase it to 128, etc. But this is not what I want to show you. What I want to show you is this. So here at the end of the code, I am picking a random latent vector. Okay, so random latent vector of dimension equal to latent dimension. So if latent dimension is 64, I'm constructing a random 64 dimensional vector and I'm trying to use the trained decoder to produce an image, and I'm just plotting the image. Look at the image. This looks completely random, right? This resembles nothing like a fashion, a wearable thing. This difference will be even more pronounced if I change the fashion MNIST dataset into MNIST dataset. So here, let me change it to MNIST. And let me show you the originals, the reconstruction, and the reconstruction using random latent vector. Okay, here it's in this notebook is the decoder taking the same point from the latent space encoded by the encoder. Yes, for reconstructions, yes. But for the last block, which is the random reconstruction, the vector that is being selected is a random vector. But the image reconstruction, the two rows which I showed you, in that we are picking the same vectors. So here again, mean squared error is 0.01. So what this means is, on an average, each pixel has only variation of 0.03. And pixel values can be maximum of 1, right? So percentage wise, it's, in my opinion, it's like around 3 to less than 5%. Roughly per pixel, the variation is only 3%. So that is what mean squared error of, actually it's a mean of squared of errors. So percentage would be even square root. So the error between pixel value is square root of 0.03. That would be square root of this will be 0.5-ish, 0.55 or something like this, because 0.5 multiplied by 0.5 is 0.055 perhaps, 0.03 raised to 0.5. 0.17. Okay, all right, my bad. 0.17. So on an average, pixel value of each pixel deviates by around 0.17, where the actual pixel scale is somewhere between 0 to 1. So if a pixel value was 1, the value can be up to, it could be like 0.83. So it's like a 17% variation, something like that. So just to give you an idea of what does the mean squared error of 0.01 mean. But look at this. Look at the originals. So top row are original images. Bottom row are reconstructions. Reconstructions make sense, right? Reconstructions are looking very similar to input images. However, look at this now. Look at the reconstruction using random vector. This is using a random vector. It resembles no MNIST image. This is nothing like an MNIST image. And I can run this multiple times. Each time it will produce a random vector reconstruction, and each time it is a meaningless image. So this is the problem with autoencoder. Now let's discuss what exactly is variational autoencoder and how does it solve this problem. So in variational autoencoder, the main thing is, the reason why I wanted to introduce variational autoencoder is because I eventually also want to teach you diffusion model, and variational autoencoder understanding lays a lot of groundwork behind diffusion models. So if you understand variational autoencoder, that's a great step towards deep generative models like diffusion model. The main advantage of autoencoder is in its compression. So if you want to compress your data in a certain lower dimensional variable or a lower dimensional space, then autoencoder is used. In variational autoencoder,
we introduce something called latent space, but with a probability distribution. So this is the architecture of variational autoencoder, but I will explain what this means. So this is autoencoder, bottom one. Top one is variational autoencoder, and I will show you what this mu, what this sigma means. All right. The paper that introduced variational autoencoder is super famous. It has 50K or 55K, something like that, that many number of citations. This first author, Diederik P. Kingma, he's extremely famous. He's also the main author behind the model, the optimization Adam. And that has revolutionized deep learning as we know today. And his Google Scholar, if you visit, he has almost like 300,000 plus citations, which is very big. So this is the Adam paper in which he was the first author, and that paper alone has 240-ish thousand citations. His second most famous paper. So in these 2 years, he was ultra productive. And so just to make sure that you know who worked behind this. The paper is extremely mathematical. It has a lot of ideas from probability, Bayes theorem, etc. discussed. But today we will try to understand the variational autoencoder from more of an intuitive point. If we were to construct variational autoencoder, how will we define the loss function? And within that, a lot of understanding of the math behind variational autoencoder will automatically come. So these are the differences between VAE and autoencoder. So in autoencoder, as I showed you, it's directly running a deterministic mapping, meaning one input is always mapped to one single latent vector. And similarly, one latent vector is directly mapped into one reconstruction. In variational autoencoder, we are performing a probabilistic mapping into latent space, meaning a given image can be mapped into within a region of a space. It can be mapped into anywhere. So technically, the input image is mapped into a something like a normal distribution. From that normal distribution, we will sample a point, and that point is what we use for reconstruction. I will show you this in a moment in a diagram. You will understand it much better. Then the main purpose of autoencoder is compression, denoising, etc. But latent space itself, as I showed you, it has it's irregular and it's not very organized. There is no such thing that this entire region is dedicated for handwritten digits of 3, this for digits of 4, etc. There is no such thing. In VAE, on the other hand, the latent space is regularized. In autoencoder, one thing I mentioned is a little bit wrong. I should not say that it's completely disorganized. That is not correct. If you, in general, plot in autoencoder, if you make a plot of, let's say, all the handwritten digits of 1, all the handwritten digits of 3, you will, of course, see clusters. So I will show you one image of such clusters. So see this. So these are created using a latent dimension 2 for different handwritten digits. And you can definitely see that there are clusters. Okay. But it does not mean that if I pick a point from here, so there is no guarantee that that point will map to digit 1. It can be completely different. There is no guarantee that something which I pick from here will map to a point like digit 0. There is no such guarantee. So although when you convert your input images into latent space, you may seem like, okay, there is good clustering, which means the space where the clusters belong may have some meaning. That is not the case. Now, in autoencoder, what we are trying to optimize is reconstruction loss, which is the mean squared error loss, where mean squared error is forcing the decoder to directly copy whatever the input is. So if input image has certain pixel distribution, the output should be almost as close to that as possible for you to minimize the mean squared error. And autoencoder is not a reliable generative model. It's a good compression model, but not a generative model. But on the other hand, variational autoencoder can generate new data. I will show you that. And the optimization, which is the reconstruction, actually has 2 terms. One, and I'll explain what those 2 terms are, but it's not directly penalizing the model for not performing a perfect reconstruction. That is what variational autoencoder does. And I will also explain what does this latent space regularization mean. So latent space is very disorganized in autoencoder. In variational autoencoder, there is a regularization happening so that latent space, different regions in latent space actually mean something.
So we'll discuss all of this when we are looking at the architecture. So just look at this diagram. In autoencoder, a digit like this is directly mapped into this region, this point in the space. That point in the space, if you are reconstructing, you will get the image back. If the model is very well trained. So if the encoder and decoder is trained for many epochs, and if the latent space dimensionality is not too small, the reconstruction will look very close to the original input image. In variational autoencoder, what we do is, just please pay close attention here. What we do is, we do not map this input image. Now this x-axis, y-axis in green color is the image space. And of course, as I mentioned, image space in the case of MNIST has 28 by 28, which is 786 dimensions. This image from the image space is not directly mapped into one single point from the latent space. What we do instead is, this point is mapped into a Gaussian distribution of certain mu and certain sigma. So Gaussian distribution, as you know, will look like this graph in one dimension. So this is what is Gaussian, an inverted bell-like curve. It means, what this means is, it has a mean value, it has a standard deviation, 2 standard deviation, 3 standard deviation. So, you know how the Gaussian distribution looks like. So here you are mapping the image from the input to a Gaussian distribution of mean value mu and standard deviation sigma. Now from that Gaussian distribution, you will randomly pick a point. If you randomly pick a point from a Gaussian distribution of mu, mean value mu and standard deviation sigma, you are very likely close to a pick, probabilistically, you are likely to pick a point closer to mu, right? So if your probability distribution is something like this, and if you pick a random point from this distribution 10 times, where are the points likely to be concentrated? Do you think those points will be likely concentrated far away from the mean? Or do you think those points which we sample will be closer to the mean? The points will be obviously closer to the mean, because in a normal distribution, the peak of the probability distribution is at the mean, which means not at the mean, it's closer to the mean, which means if you sample from that distribution n number of times, more than often, you will end up sampling points from closer to the mean. Some points may be sampled from away from the mean. Similarly, when you are constructing a probability distribution like this, using your point by constructing mu and sigma, and from that distribution, when you are sampling a point, you have no guarantee that the sample point is always the same point. If you sample now, you may end up sampling this point. If you sample later, you may end up sampling this point. If you sample later, sometimes the point may be far away, right? So you have no guarantee that the point which you sample from the latent space is always the same corresponding to a given image. There is no such guarantee. Then what do we do with that sample point? That sample point is now passed through a decoder to perform the reconstruction. So just pay good attention. Each image is mapped such that a Gaussian distribution is constructed. From that Gaussian distribution, you pick a sample point, and that sample point will be the point in the latent space to be mapped or to be used for reconstructing the image. Now, if you are doing this, right, for the same input image, you will end up with a different type of reconstruction because you are sampling a different point. But when you are doing this over and over for a large number of input images, the output will not be such that the input images of letter 9 is almost always something like this. There is no such guarantee. Rather, the input images of 9s might be represented by a Gaussian which lives somewhere here in the space. Input image, or somewhere here in the space, let's say. Input image of the letter 3 might be somewhere here in the space. Input image for 4 might be somewhere here in the space. We can plot and see this. So basically, what we are doing is we are forcing the input image to be represented using a Gaussian in the latent space. So input image is not one-to-one mapped to a point, but it's rather mapped to a distribution. Now what we are doing is, from that distribution, we will sample a point. Using that sample point, we will construct the reconstructed image.
which means now we have two things to think about. Okay, there is one more question. For each digit, a separate distribution is created. In fact, for every image, a separate distribution is created, not even for each digit. For every single image, you predict a mu and sigma. And from that, so mu and sigma means you are predicting a Gaussian. And from that Gaussian, you will sample up a point. There is one more important thing to be noted. Okay, great question. How do we pick a random point? Great question. I'll come to that. So one more thing to be noted is that in the latent space, when we are constructing this normal distribution, so n of mu comma sigma means, or n of mu comma sigma square means variance is sigma square and mean is mu. We say that the distribution of my input points, right? So input points are the actual images of my MNIST images, but input points can be some random images also, because in my 28 by 28, which is 784 dimensional space, MNIST images are not the only images. There are a lot of random meaningless images living in the image space. But here, what we say is that the latent space corresponding to my MNIST image space will have a normal distribution such that mean is equal to 0, and standard deviation is equal to 1. So this is like a standard normal Gaussian distribution, which is centered at 0 and standard deviation is equal to 1. So what we are essentially trying to do is, whenever we are trying to predict mu and sigma, we want to predict ideally such that mu is closer to 0 and sigma is closer to 1. There are a few questions. Just for clarity, now latent space would be a collection of Gaussian distributions. Yes, latent space will be a collection of Gaussian distributions, but because we want those Gaussian distributions to be a standard Gaussian distribution or normal Gaussian distribution, the mu will be forced to be closer to 0 and sigma will be forced to be closer to 1. So now there are two things we want to enforce here, right? One is the reconstructed image should be closer to my original image. That is one thing. If this is not looking like a 9, then there is no point in even doing this. So of course, the reconstructed image has to be looking similar to my original image. Second thing is, we want to penalize the model, right? We want to penalize the model for predicting a Gaussian distribution with mu and sigma as the mean and standard deviation if it diverges too much from the standard normal Gaussian distribution. Meaning, if the model predicts something where mu equal to 5 and sigma equal to 25, model has to be penalized, because this Gaussian, whose mu is 5 and sigma is 25, is very different from, so n of mu comma sigma square, we want to be making it as close to n of 0 comma 1 as much as possible. So we penalize the model if the model is not able to do this. Okay, so mu comma sigma penalty. So think about this. We are penalizing variational autoencoder for two things: one for making poor reconstructions, and one for making poor predictions, meaning one for making predictions of Gaussian distribution which are far away from standard normal Gaussian distribution. Now, let me ask you, how do you penalize the reconstructed image? So now we are discussing the loss function. How do you penalize the reconstructed image? We already discussed this. Obviously, mean squared error. You compare pixel by pixel, take the square of difference of pixels, add them up, divide by number of pixels, for sure. How do you penalize n of mu comma sigma square being different from n of 0 comma 1? How do you penalize this? Could you penalize something like, you want mu to be closer to 0 and sigma to be closer to 1. So can you do something like mu minus 0 the whole square plus sigma minus 1 the whole square? How about this? What about this loss function? So my total loss function will be L equal to 1 by n, sigma I equal to 1 to n,
yi cap minus yi the whole square plus predicted mu minus supposed to be whatever is the mu, which is 0, plus predicted sigma minus sigma that is supposed to be the whole square. How about this? Can I do something like this? I mean, logically, you can. There is no problem. But the only issue is when you are doing this mu minus 0 and sigma minus 1, you are not comparing two distributions. Here you are comparing two distributions. You are not just comparing two numbers. You are not comparing mu to 0 and sigma to 1. What you want to compare is this distribution you want to compare against this distribution. This is where the term KL divergence comes. Can you please try to recollect where did we discuss about KL divergence before in this course? We had discussed about KL divergence once. So KL divergence is the way to compare how close or how far away are two distributions. KL stands for Kullback-Leibler divergence. It is a way to compare two distributions. If the two distributions are exactly same as each other, if these two overlap and they are completely same as each other, KL divergence will be 0. Otherwise, it will keep increasing. KL divergence also has a very nice formula. So if you are comparing the reference distribution P against the distribution to be compared against Q, so in our case, the reference distribution is n of 0, 1, and the distribution you are comparing that, a distribution that you are comparing with the reference is n of mu, sigma or mu, sigma square, if you want to mention in terms of variance. Then P is this 0, 1, the one with mu equal to 0 and sigma equal to 1. Q is the one with predicted mu and predicted sigma. Then if you have discrete number of points, meaning if in your probability distribution, it's not a formula, but you have a bunch of actual numbers. So you have a probability distribution, let's say P equal to 0, 0.1, 0.2, 0.7. And let's say Q equal to 0.7, 0.3, 0, last term is 0. Then this you can compare using this sigma formula. But if it's a continuous distribution, you can simply integrate it. So instead of sigma p of x log p of x by q of x, you do sigma p of x log p of x by q of x dx. And now P is the reference distribution, right? The good thing is, in our case, since it's a Gaussian distribution has a formula. So this is the formula. Gaussian distribution has this formula: 1 by sigma square root of 2 pi exponent of minus half x minus mu by sigma whole square. This is a very standard formula. The good thing is, since both of these are Gaussians, we can construct the KL divergence formula in this way. So KL divergence between P and Q, actually P is the reference. So actually this should be over here and this should be over here. This is a mistake. So P is my reference and Q is my distribution that I'm comparing against my reference, is equal to half times mu square plus sigma square minus log of sigma square minus 1. This is the formula for comparing the two Gaussians, the KL divergence laws. Now compare this against the formula which we just discussed, the naive formula which we discussed. Where was it? This one. This will be mu square. This part will be mu square plus sigma square plus 1 minus 2 sigma, right? Just compare this against. So mu square plus sigma square, then plus 1 minus 2 sigma, right? That was the formula which we would have ended up with if we were not comparing the two distributions, but rather we are just comparing mu and sigma. Now look at this. They are very close to each other actually. Technically, you could use this formula also, but then you will not be strictly comparing the two distributions. You will be directly comparing mu and sigma against 0 and 1. But when you are actually comparing two distributions, the formula that you will end up will be something like this. The derivation of this is a little bit not involved. We don't have to do it right now. Now the total loss will be the mean squared error loss, which is also there in autoencoder. So this is the MSE plus the KL divergence loss.
And this KL divergence loss basically regularizes the latent space, meaning it gives the latent space provision to produce a probability distribution corresponding to an input rather than one deterministic point. So it makes the space more smoother. We will see what this smoother look like when we produce an output image, right? So this is the final variational autoencoder loss. Now I want to also discuss one more thing, which is the encoder decoder architecture before discussing the, before doing the coding. So let's look at how the architecture would be. Let's say my latent space is this, and let's say I want my latent space to be 16 dimensional. So what would this be? In a neural network, what would this 16 dimensional thing look like? A layer with 16 nodes, right? Something like this. 16 nodes, okay? Now, this is my latent space. So I'm denoting it by Z. So before the latent space, I will have a hidden layer. This hidden layer, let's say it has 256 dimensions. Before the hidden layer, I will have a flattened layer of my inputs, which are of 784 dimensions, correct? So it's basically like a multi-layer perceptron, and this will be fully connected. This will be fully connected. Only difference is here there will be ReLU activation. Okay. So after the weights are being applied, there will be ReLU activation. And here there will be my input image of 28 by 28 pixels. So you are flattening the 28 by 28 pixels. Then there are weights here, W11, W12, etc. So there will be a matrix which multiplies, whose dimension is of 720, 84 by 256. In Python code, okay, why are we grounding? There's a question. Why are we grounding the standard? Why are we grounding to standard Gaussian? This will collapse all distributions in the latent space, correct? So what we are deliberately trying, that's an assumption made actually. In reality, what would happen is your image space would be something like this. Let's say image space is this. I am sampling an image from here, okay, from this space. My latent space might look like this, some random distribution. So if I were to pick, and let's say this is the space where all the MNIST images are residing. If I were to map all these MNIST images into my latent space will have some random shape. Now what the assumption that we are making is this latent space actually is assumed for simplicity that it looks like a Gaussian, which means it has a mu and a standard deviation. So, so that we can have a easy way to map from my images to this distribution, and then from this distribution to image in case of regeneration. So what the encoder does is it creates a mapping from this P of X, which is a probability distribution, to P of Z, which is another probability distribution, where X is the space where you have input images, Z is the space where you have latents. This is what encoder does. What the decoder does is it learns to map something back from this latent space distribution back into your image space. And we don't know how this space looks like because we don't have all the handwritten digits in the universe available to us. There are many different ways in which handwritten digits can be made, which means P of Z also, there is no way for us to know what this random shaped P of Z may look like, because we cannot obviously construct corresponding Z for every single X in existence. We can't do that. So for simplicity, we assume that the latent space distribution is like a Gaussian, and that too standard Gaussian. So it's an assumption made to make the calculation of this simpler. Now, one more thing is, so this is the encoder, and in encoder you have ReLU. Now this is latent space. After latent space, you will have the decoder. So decoder, again, this layer will have 256 nodes. And then the last layer will have 784 nodes. And this will all be fully connected. This will be fully connected. There will be ReLU activation here. There will be ReLU activation here. And one more question I have is, what would be the activation at the last layer? Over here, right after this 784 dimensions, what will be the activation function used? Will it be ReLU? So think about it. If we use softmax, what would happen? Many of you are saying softmax based on kind of impulse. But think about it. If I have softmax, see, this is a 784 distribution. Every pixel matters here, right? We are not trying to find the one single pixel with the best possible value. Just think about it. We want all pixels matter because all pixels play a role in creating the reconstruction. So it's not like we want to find the one pixel with the best probability. It's not what we want. What we want instead is the values of every single pixel should be within a range of 0 to 1, correct? So every pixel should be 0 to 1. The problem with ReLU is that ReLU is unbounded. ReLU's value can be less than 0. Sorry, it can't be less than 0. It's from 0 to plus infinity. So the better activation function to use at the last is sigmoid, because sigmoid looks like this. Sigmoid's value is bounded between 0 and 1, irrespective of what the input is. Input can be from minus infinity to plus infinity. Tan h we cannot use because tan h will be from minus 1 to plus 1. So the problem with ReLU is that in the previous layers we used ReLU, but then that is because unbounded activation functions have expressive power. However, the final output that we want is not unbounded. It's a bounded output. So we use sigmoid in the last layer. Okay, so just note that. So if you now look at the overall neural network architecture for this, it's very simple. The only additional thing we need to know is where exactly is mu and sigma coming into picture. So here we mentioned about latent space Z, but we did not talk about mu and sigma. So what is actually done is there are two layers. So from encoder, so this is the first layer of encoder, this is the hidden layer of encoder. Then in the latent space, actually there are two parallel layers. This layer has 784 nodes. Sorry, not 784. Let's say latent space is 64 dimensions, 64 nodes. This has 64 nodes. This is fully connected to this. This is fully connected to this. So this will be 256 nodes. This will be 784 nodes. And these 64 nodes will represent mu. These 64 will represent sigma. Okay, so these are two disconnected nodes. So two disconnected layers within the latent space. So whatever is there in these 64 nodes will represent mu. Whatever is there in this will represent sigma. And then we will construct the KL loss based on what this mu and what this sigma look like. That is the first thing. Second thing is, now to predict my reconstruction. So my reconstructed image will be, let's say, 6 or whatever. I need to start with some random point in the latent space, right? Some random Z. How do I randomly sample from a distribution? My distribution looks like n of mu comma sigma, correct? It's a normal distribution whose mean is mu, standard deviation is sigma. I need to sample from this, correct? Yeah, I'll explain once again. We need to first predict mu and sigma. And then from that distribution, I need to pick a random latent vector Z. And this random latent vector will be finally used for reconstructing my original input image. Now, my question is, how do you sample? How do you get this Z? One way to sample is you use some random number generator and or whatever numbers you have in your mu comma sigma space. You randomly pick a number. The other option is any number which you have in a normal distribution. You can express it as, so this number you can express it as mu plus 1 standard deviation, or mu plus 2 standard deviation, or mu plus epsilon standard deviation, where epsilon is a variable. So any number in a distribution, I can represent by saying this number is equal to mu plus some variable multiplied by standard deviation. So if the variable is exactly over here, then it will be mu plus 0 standard deviation. And if mu is also 0, this will be 0. If the randomly picked number is far away, then it will be mu plus, let's say, 1000 standard deviation. It is very far from the mean. So essentially, all we need to do is define a random variable epsilon
which is sampled from a distribution like this. So we sample a random number called epsilon, and then we say my number that I am picking, which is z, is equal to mu plus epsilon times standard distribution. The reason why this is done is when we are constructing the loss, right? As you know, the loss is dependent on, it's a function of mu and sigma, right? Which means I should be able to, and it is also dependent on other things, but it is also a function of mu and sigma. So for constructing gradient descent, I should be able to do dou L by dou mu, or I should be able to do dou L by dou sigma. I want to be able to do this. But if I am randomly picking a variable and saying my z is equal to some random number epsilon, then my z is not dependent on mu and sigma. But here, if I say z is equal to mu plus epsilon times sigma, now my z is dependent on mu and sigma, which means I can define eventually some parameters which will be like, so let's say dou L by dou mu is equal to dou L by dou z multiplied by dou z by dou mu using chain rule. Or I can say dou L by dou sigma is equal to dou L by dou z multiplied by dou z by dou sigma. So I can have a differentiable function, which means I can perform backpropagation. So just to reiterate, we construct the neural network, the decoder, such that in the first layer, I have 784 nodes. Second layer is a hidden layer in which I can have variable number of nodes. And third layer is also variable, which is the latent space. But in the latent space, I am predicting two things, mu and standard deviation. So mu will be, again, 64 dimensional. Standard deviation will also be 64 dimensional. And these are fully connected. And these are also fully connected. Now, from this mu and sigma, I will sample something such that my z is equal to mu plus epsilon times sigma. The dimensionality of this z will also be 64. So all of these are 64 dimensional. Then I will project the 64 dimensional thing vector into 256 dimensional hidden layer. Then from that, I will project it into 784 dimensional layer. From this, basically, I have my image reconstruction. Then I have two errors. One error is by comparing the input image to the output reconstruction. That is the mean squared error. Another error is by comparing this predicted mu and predicted sigma, which is n of mu comma sigma. We are comparing it against n of 0 comma 1 and constructing the KL divergence loss. And then the total loss is MSE plus KL divergence loss. So this is the total loss which is used for defining the architecture of variational autoencoder. Mu and sigma, how are they calculated? They are just calculated using the neural network. They are the parameters in these neurons, basically. So if latent space is 64 dimensional, mu is 64 dimensional, it's calculated here. Same for sigma. So they are basically learned through the neural network. So initial mu and sigma will be random because the parameters will be random. Eventually, it will become closer and closer and closer to 0 and 1. But not extremely close, but closer and closer because there are two losses, right? If you try to minimize KL divergence loss, maybe your mean squared loss will increase. So you cannot minimize both. You are trying to minimize the sum of both. So there is no guarantee that KL divergence will be such that mu and sigma are close to 0 and 1. There is no such guarantee. Because maybe if you make mu and sigma extremely close to 0 and 1, your mean squared error might increase a little bit. So during gradient descent, the network will figure out what is the best way in which the total loss can be minimized by minimizing MSE as much as possible and minimizing KL as much as possible. All right. So now I think we can code, and during the coding, all the rest of your questions will be answered. Okay, there is a question. Since here image size is small and dense representation will work. However, for higher resolution, we can use convolution encoder and decoder. In that case, latent space can be of higher dimension. Or it has to be single dimension vector. How will it be? So latent space is already higher dimensional. If you think about latent representation space is already 64 dimensional or 128 dimensional, right?
but it's a space of vector. Even if you think about a three-dimensional, like an RGB image, that also you can think of something that is, so let's say this MNIST was RGB, okay, 28 by 3. You can say that this is represented in a space whose dimension is 784 multiplied by 3, whatever that number is, 2100 plus, whatever that is, right? So just by having additional channels, no complexity is arising other than your computational cost increasing. So here we are essentially performing operations similar to CNN, except convolution operation is not there. So it's not a convolutional neural network. It is like a multi-layer perceptron. Then there are. So finally, if you think about it, the latent space is at the end of the day a space, multi-dimensional space where vectors can live. That's all. It doesn't matter whether the input image is color image or black and white grayscale image. Okay, let's now start coding, and we can take up some more questions in the middle of the day. So please open an empty, Google Colab. And just name it as anything, VAE from scratch. I will share this with you in case you want to follow my code as such, but there is no need for that. I mean, this time we are not using any pre-trained weights or anything. So variables, you can use any variable you want. All right, so let us start with imports. The first is import torch for PyTorch, then import torch.nn as nn, which will be using during coding the class for variational autoencoder, as we have always been doing. Torch.optim as optim for defining optimizer. Then from torch vision, import data sets, which will give us access to MNIST, fashion MNIST, etc. And transforms for performing transformations such that you can convert images into tensors. Then from torch.utils.data, import data loader. This is for creating batches of data. And then finally, for plotting images, import matplotlib.pyplot as PLT. NumPy is not needed. Fairly straightforward. These are the only imports we need. And then we can just define the device. Device equal to same thing. Device equal to CUDA if CUDA is available, else CPU. Here I want to pick something like maybe V6 6E-1 TPU. You can pick anything. This code is going to be very simple, so no need to, no need to have any GPU. Oh yeah, torch.utils. I was having an extra space here. My bad. All right. So these are the imports and device. Now we can have our code block for creating batches. We can say batch underscore size is equal to something like 128. Then transform equal to transforms dot compose. And inside this, the only transform we are going to pass is transforms dot toTensor. So earlier we sometimes used to do transformations like normalizing using mean standard deviation, etc. Here we are not doing that, just converting the images into tensor format. Then we say train underscore dataset equal to datasets dot fashion, or let's start with MNIST actually, not fashion MNIST. MNIST of the folder to download is root equal to ./data. So this is where our data set will be downloaded to. And train equal to true. This is training data. Download equal to true. And then transforms. For transformations, we'll use this transform. So transform
equal to transform. Maybe to reduce confusion here, I can call it as data underscore transform. And this is what I'm passing here. Then this I'll keep as a third argument. That is usually what is done. Doesn't matter. Then here we don't really need validation data because we are just looking at the reconstructions directly. So we don't necessarily need the validation data. We can just use only training data to just see how the reconstructions look like in the training. Train loader is the dataset loader for train. So data loader of, and here we have to pass dataset, and dataset is nothing but this train dataset. Then we have to pass batch size, which is defined by this. So batch underscore size is equal to batch size. Then shuffle equal to true, which you may or may not define, not needed, but let's keep it since we have been doing this in every code. That is the train loader, and that's it. So this is how you create batches. Now comes the main part, coding the VAE class. So first we can define a latent dimension, latent dim. Let's say this is 64 dimensional space, latent dimensions, okay? And we can say class VAE of nn.module so that we can inherit properties from nn. Define underscore init underscore and self we pass here. Rest of the things, whatever we want to pass, we'll figure out. And then for inheriting properties from my parent, super, then self dot underscore init. Actually, we don't have to pass this. This is enough. Then we can write the encoder, then we can write the decoder, then we can write the forward pass. The forward pass will be a function like this, define forward self comma x, right? Inside this one bunch of things we will write. So first let's write the encoder. In encoder, we start with the image. So first is a fully connected layers going from 784 dimensions into 256 dimensions, which is the hidden dimension. So here I can say input dim equal to 784. This is the MNIST 28 by 28. Hidden dim, let's keep it as maybe 256, and latent dim equal to this latent dimension. So I'm just passing this variable here. So in encoder, self dot fully connected neurons 1 in layer 1 is equal to nn dot linear. And this is from what to what? What are the two arguments that I should pass here? I am going from input dimension to hidden dimension. So please note, anything after nn dot is trainable parameters. Then self dot fully connected to, actually there is fully connected. We don't have to say fully connected to. Instead, it's better to say fully connected for predicting mu and fully connected for predicting standard variance. So what we are actually going to predict is this, not standard deviation, but this term. So this, you see this log of sigma square, basically this is log of variance. So what we are going to predict is log of variance. I'll tell you the reason why we are doing this. The reason why we are doing this is the output from a layer of neurons can be, if ReLU is there, the output will be definitely positive. But otherwise, the output can be positive or negative. So let's say we were trying to predict sigma square directly. Then we know that sigma square is always positive, which means we have to enforce the neurons to always output positive values. But logarithm of sigma square
can be positive or negative, because if sigma square is less than 1, logarithm of a number between 0 to 1 is spanning from minus infinity to 0, correct? And if the number is greater than 1, logarithm can be greater than 0. So by predicting logarithm of sigma square, we don't have to force the neural network to necessarily predict positive values. So that's the only reason why we are trying to predict this term, logarithm of variance. So from if we say we are predicting log of sigma square, how do we get to sigma? And let's say I'm calling this as log var, logarithm of variance. Exponent of log var is equal to what? Sigma square, or yeah, this is equal to variance. So to go from log var to variance, all you need to do is take an exponent. So if you predict this logarithm of variance, you can get sigma square or sigma or any quantity you want. So what we are going to do here is we will predict mu as such, but here we will say we are predicting logarithm of variance. So now mu is nn dot linear from what to what? What would this be? Hidden dimension to latent dimension. So hidden dimension, comma, latent dimension. And what about this? What about self dot fc underscore log var? Same thing, because it's another set of fully connected neurons where the number of nodes are going from hidden dimension to latent dimension as well, right? So these two, but look at this, these two are now in parallel. Mu is predicted from hidden layer. Logarithm of variance is also predicted from hidden layer. All right, so that is the encoder. Decoder is simple. Decoder is self dot fully connected 2 equal to nn dot linear. And here we are first projecting from latent dimension to hidden dimension. And in the next layer, self dot fc3 is we are going from nn dot linear hidden dimension to output dimension. Output is simply same as input dimension. So I can just say, because the final predicted image we are directly comparing with the input. So final predicted image will also have 784 by 784. So here I can say input dimension, which is 784. That is decoder. Now we need to say self dot ReLU, because we'll have to use ReLU multiple times, is nn dot ReLU. And at the last layer, we'll be using sigmoid. So nn self dot sigmoid equal to nn dot sigmoid. Okay, there is a question. If images are of higher resolution, then does it mean I would need more hidden layers? Not necessarily. I can, like, to preserve to make sure that there is no over compression, right? Yeah, probably. Maybe you can add more hidden layers, and using that you can ensure that. Otherwise, what if you are jumping from 3000 as the input dimension into 256? There is a lot of compression happening in just one layer. But I don't think it's needed. You can just have one hidden layer also. But in general, neural networks, the more layers there are, the more the expressive power. Okay, that is encoder, decoder, and now before forward pass, we need to do one thing, which is define encode. So this is the forward pass through the encoder. Then we can have a forward pass through the decoder, which is decode self comma x. And we will also need before this the reparameterization. And what is reparameterization? Nothing but picking z. So you're sampling z from your standard from your mu comma sigma distribution. So reparameterize, that's the official term used in the paper. It's not a term that I invented. The rise here self comma mu comma log var, logarithm of variance. This will be passing. And in decoder, we are technically passing z. In forward pass, this is correct.
Now we need to write these functions. So first encoder. So encoder will say h is equal to, which is hidden, equal to self dot ReLU of self dot fully connected in layer 1 of input, which is x. Now this hidden is projected into mu and logarithm of variance. So mu equal to something, logarithm of variance is equal to something. And what is mu? Mu is self dot fully connected layer for mu of h. Similarly, logarithm of variance is self dot fc underscore log var of same h. Then we can say from this we return mu and logarithm of variance. These two things we return. Then in reparameterization, we say standard deviation is equal to torch dot exponent of 0.5 into log var. So this is essentially finally taking square root of exponent. Then we are sampling from the same distribution. So epsilon equal to torch dot random number like standard distribution. Basically, this rand n like means if this standard deviation is coming from a distribution, we are picking another epsilon, which is supposed to come from the same distribution. So rand n like is to sample another random number from a distribution which is very similar. Then we say z is equal to mu plus epsilon multiplied by standard deviation, and then return z. So now this z is the random z which we sample from our distribution resulted from the input image. Return z. And then what will decoder do? Decoder will say the hidden layer output is self dot ReLU of self dot fc2 of z, and then final output is equal to self dot sigmoid of self dot fc3, I think, yeah, fc3 of h, which is this h, and then we return the output. So this output is now the final reconstructed image. Now we have to do a full forward pass through the whole thing. Then we say mu comma log var equal to this one. So self dot encode, then x z equal to self dot reparameterize of mu comma logarithm of variance. And the last thing is the x reconstructed which is the reconstructed image, is equal to self dot decode of z, and then I can simply return the reconstructed x, which is the final image that is reconstructed. So fairly straightforward. Now let's run this to see if syntax wise everything is okay. Looks like it's fine. Oh, one more thing we might have to return is mu and logarithm of variance also we should return. You know why? For calculating loss. If you don't return this, loss cannot be calculated. So just make sure this is also returned, because outside this class, we need access to the mu and logarithm of variance for the KL divergence loss. So speaking of loss, now it is time to code the loss. Coding the loss. So define VAE underscore loss. Here we are passing reconstructed x. Then we are passing x itself, so that we can, so these two are compared for mean squared error, these two guys. And then we are passing mu and logarithm of variance. Then we say reconstruction recon underscore loss is equal to nn dot functional then dot binary, then nn dot functional, then dot binary, 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 then dot cross underscore entropy and recon underscore s. We could simply, let me ask if there is a direct MSE function or not. Is there an MSE function like this? Torch dot nn dot. Okay, so let's then try this. Nn dot functional dot MSE loss, then reconstruction comma x. So those are compared, and then KL underscore loss is equal to this was a formula. The formula was half times, I think, mu square plus sigma square minus logarithm of variance minus 1. So 0.5 multiplied by mu square plus sigma square, which is logarithm log_var dot exponent, that itself is sigma square. So mu square plus sigma square minus logarithm of variance, which is log_var, and minus 1. This was the formula. Then actually I should do torch dot sum. So 0.5 multiplied by torch dot sum of all these guys. Okay. And then I can return the total loss is simply this plus KL loss. So this is the final loss function. There is a question, is the formula for KL in this case of normal distribution comparison predefined as you shown from the internet? So KL divergence loss formula is derived. So this is the actual integral. Okay. To this integral, if you substitute the fact that P of X is normal distribution like this and Q of X is normal distribution like this, and if you derive, you will end up with this formula. So we can sit and derive it, but then we'll be digressing too much from our core idea here. But essentially, this formula is resulting from the fact that our distributions are two different normal distributions, one's with mu equal to 0 and 1, the other one with mu equal to mu and sigma equal to sigma. So, but this formula does not apply if the two distributions are not Gaussian distribution. Just note that. But yeah, this formula I directly got from the internet. I did not derive it here, but it's not difficult to derive as well. It's because it's all deterministic. It's a well-defined formula which you can substitute in the integral. Integral, of course, will give you some pain, but if you sit down and do the integration, you will end up with this formula. Okay. So this, you can just run the variational autoencoder loss function, and now we can define the model. So model equal to VAE, we had defined this class. We can also say to device just to make sure that model is also using the same device CPU or GPU as the earlier ones. Then optimizer equal to optim.atom with a capital of, and what we are optimizing is model dot parameters. And learning rate also we can define to be, let's say, 1e minus 3. So this is just the optimizer and model, and now we can do the training loops. So first we say epochs equal to something like 5 just to make it fast. Then model dot train to keep the model in the training mode instead of in the eval mode. Then say for epochs, for epoch in range of epochs. So first we define a total loss function, a total loss variable whose value is initially 0. Then for x comma dash in train loader is where my batches are there. X equal to x dot view of -1 comma 784 dot to device. So please note, the reason why this line is written is because
my batches are like this. My batch size is 128 or something, right? So my batches are like 128 comma channel comma 28 by 28. This is how this will look like. My data will look like batch dimension, channel dimension, width and height dimension. What I actually want is in my fully connected, sorry, in my flattened layer, I just want 784. And then I'll have a batch dimension or whatever this dimension, whatever this number should be. One thing to note here is if my input images are let's say an exact multiple of 128. So let's say I had 1280 images in the input. If I divide it into a batch size of 128, I'll have 10 batches whose number of images are exactly 128. But what if I had only 1279 images? Then my batches will be such that last batch will not necessarily have 128 images, it will have only 127 images. So I cannot hard code 128 here. But if I say it is minus 1 comma 784 with used along with view function, automatically Python will calculate what the number here should be, whether it is 128 or 127 or whatever that number is. So that is why we use this view function. It basically automatically calculates whatever should be the replacement for this minus 1. Then optimizer dot zero underscore grad. This is to make sure that we are we are not storing the gradients from the past batches. Optimizer. There should be an I here. I'm missing an I. Then x underscore reconstructed is equal to and yeah, this comma mu comma log variant. Both these three things are output from the model. So equal to model of x. So from the model, these three things are coming out as output. Then we say loss is equal to VAE underscore loss. And into that, I pass these things along with x. So x reconstructed, comma x, comma mu, comma logarithm of variance, because these four inputs are being expected. Then we say loss dot backward. So loss. So this optimizer for dot zero grad is done for every batch separately. So if we put it outside here, it will be only applied for the first batch. It won't be applied for the rest of the batches. Loss dot backward, then optimizer dot step. So this is the backward propagation. These are standard. We usually don't write this, but today, since the model part was anyway easy, total loss equal to total loss plus this loss dot item. And then we come out of the loop, and then we want average loss. Average loss is total loss divided by total number of batches. So equal to total loss divided by, and how do you get the batch size? Length of train loader. And then we can print it. And we can say print epoch, and epoch number is epoch plus 1, because this epoch variable will start from 0. So epoch number is epoch plus 1. So 1 out of all the number of epochs. So epoch's value is 5. So this will be 1, 2, 3, 4, 5 sequentially. It will be displayed. And loss is average underscore loss with 4 floating point precision. I hope the syntax is correct. Now we can hopefully run this. Okay, let's run this and see what happens. If there is any error, we'll see at that time. Okay, it seems to be running fine. Just some bracket is missing. That's all. That's okay. Okay, so the loss is coming pretty much down, and now we can just plot the image. So for plotting the images, I'm just going to copy the code because I don't have to write this piece of code. I don't want to write this piece of code. This is just plotting the sample images. So here what we are doing is we are picking 8 images from our sample, from our training, 8 random images, and we are plotting those 8 images and comparing it with the reconstruction. Okay. So just look at this.
So these are now the images and these are the reconstruction. Very bad, right? I think what we are missing is probably number of epochs we can increase. What else can we do? I think everything looks good. Let me just run this once more. Because the reconstruction is really bad. Okay, this is really poor reconstruction. I was in general getting reconstructions like this for low dimensional latent space, but here my latent space is not so small. Maybe what I can do is increase the epochs and increase the latent dimension. Please try to run this yourself and let me know what output you are getting in terms of reconstruction. Let me try actually binary cross entropy loss. Maybe that will converge better. Let's see. This one. Because here it does not seem to converge at all. So yeah, loss. So my loss here is, okay, here there is again, clearly something is wrong. Let me check once more. So I was able to get losses like 0.01 or something. Our loss was like 0.06. So just wanted to see if reducing it further will improve the accuracy. But let's see what else am I missing here. nn.functional.binary cross entropy, that looks fine. KL divergence, so mu raised to 2, with this we are doing. Okay, so perhaps instead of doing this, should not make any difference, I hope. And logarithm of variance dot exponent. Let's run this once more. Do you guys see any obvious mistake? I'm not seeing any obvious mistake, but I'm sure there is something, because loss, this high of a loss is not at all sensible. Log, I have not missed, I think. Let's do one thing. Let's run this code and come back. The scale divergence multiply by -1. This one, right? I don't think so, because
The formula is this. Let me see. I don't think so. So this is the exact formula that I'm using. Half times. You can write it as minus half times, but then all the things inside will be flipped by -1. So I think the formula is correct. Where else can be the mistake? Let me check this training loop part. I'm not sure if I'm making any silly mistake. Let me just copy paste this. Okay, now the loss has decreased. So clearly there was some issue with my previous training loop. Let me just go back and see. This is my current training loop. And this is from my actual working code. Okay, this is the mistake. The average loss when I'm dividing, I should do train loader dot data set. Obviously, yes. This is the mistake. So I'm not dividing the length by the length of train loader, the actual data. VAE loss, please check. Okay, I think if I change this now, if I run, hopefully it should work. I think this is the only mistake that I could spot. Yeah, okay, now it's working. All right, so I was just missing this train loader dot data set. Okay, so let's just run the code once more. I'll use my now loss seems to be a bit high. I just want to try running this once on my original working code and see what kind of losses I was getting. Code is pretty much the same, but so here the number of epochs are 15. The latent space dimension is 64. All right. Okay, losses seem to be on the similar order of magnitude, so maybe it's fine. Okay, so this is my convergence now around 100, and these are my reconstructions. All right, this is good. So these are now the reconstructed images, and it's pretty good. And if you run this each time, it will pick another 8 set of images and it will provide the reconstruction. Okay. Now, one thing I want to show you is reconstruction using a random Z. That is the important thing. So it will look a little bit random. Of course, it won't be as good. So this is a random input. So here we are saying I want to pick 16 random vectors, each of whose dimension is same as latent dimension. And let's see. So it's better. It's not the best, but it's much better than autoencoder. Autoencoder was giving us things like this, if you remember. This was the autoencoder. I think this is disconnected. Okay. But this was the output of autoencoder. But variational autoencoder is giving much better output. Some of them are, not making any sense, but at least it's still looking like closer to MNIST. Now this can look even better if we do work on fashion MNIST. So let me just change this data set to fashion MNIST. And let me run this whole thing once again. So here there are a few experiments which we can try. Okay. One is changing the latent space dimension from 64 to just one dimension. What if we just did one dimension? Could you get a good reconstruction? So we can actually try that with autoencoder itself. So autoencoder, let's say my embedding. So the question is, can you compress your latent space so small and get good reconstruction? Okay, so here I'm picking latent dimension as 2. All right, in autoencoder, and I'm just running the full code. I'll show you the reconstruction once the code is done. And yeah, this is the fashion MNIST dataset. So here, these are the images. These are the reconstructions. So one thing about variational autoencoder is that it has a sort of blurring effect. The reason why this blurring effect is coming is because you might have heard about Gaussian filter itself, right? Gaussian filter it basically averages out the sharpness in the image. Here also something very similar is happening. In the latent space, the data is distributed like a Gaussian, and because of the fact that there is a distribution of the data, there are no sharp edges that are created in the output. But in autoencoder, you can have sharp edges, but the thing is, it can only produce images which are exceptionally close to the reference point. Even if you're slightly far away from the reference point, you will have very useless reconstructions. So here, these are the first row is the actual fashion MNIST data. Second row is the reconstruction, and these are for random vectors. So for random vectors from the embedding space, see, these are still meaningful. These are all reconstructed images from random input latent vectors. You see, it's not senseless; it's sensible. Let me look at the two-dimensional reconstruction. So with two-dimensional latent space, so please note this is autoencoder which I'm showing right now, not variational autoencoder. I just want to show you the reconstruction. With autoencoder, look at the reconstruction. It's not that different. And how do you make sense of this? I have a code here which I want to show you for autoencoder. So here, what I'm doing is I'm plotting the this latent space itself directly on a scatter plot. So just look at this 3, 8. They are looking very similar even after reconstruction. 5 is also, so 3, 8, and 5 are looking very similar, right? 7, 9, they are all looking very similar. So now, if I plot the reconstruction, if I plot the latent space, look at the latent space in 2D. The ones with least intersection is orange, which is digit 1 and digit 0. So digit 1 and digit 0 will never be confused, but rest of the digits have very high overlap. So let's look at digit 1 and digit 0. If I run this once again, hoping that digit 1 and digit 0 come, see, 1 is getting reconstructed really well. 0 is getting reconstructed somewhat well. But rest of the ones are, 6 and 2 are not getting reconstructed properly. 6 is getting reconstructed as something like 8. 2 is getting reconstructed as something like 8. But 0 and 1 is very good. Now, variational autoencoder, in that also, we could do the same. I think this one I will reserve for an assignment. I wanted to give an assignment of plotting the scatter plot for latent space. So here, this is the direct latent space plotted in a 2D scatter plot. My question is, what if the latent space dimension was 4 or 5 or 6 or something like that? What can we do to plot? If I wanted to have a visualization of the latent space, what could I do in a higher dimensional space? I can simply pick two principal components, the top two principal components, and plot the two principal components, right? Here I have done 3D also. So if I keep my latent space dimension as 3, it plots a 3D plot, but beyond 3, it will plot using principal component analysis, the two principal components. So this is one way to plot the latent space and see the reconstruction. So in general, you should see that the reconstruction becomes better if the latent space is having more dimensions. Why is that? Because then the loss of information is less. The smaller the latent dimension, the greater the loss that happens. Obviously, right? If the latent space dimension is 1, what does that mean? It means your entire image you are hoping to capture with just one number. If the dimension is 2, you are using just 2 numbers to capture the information in an image. So obviously reconstruction will suffer because of that. So this also, I just want to show you this 3D, 3-dimensional reconstruction. Obviously it will look better than 2 dimensions. And I will show you the latent space, how it looks like. So this is in 3D. Again, not the greatest. Many 1 and 0 are not getting confused, but remaining digits are completely getting confused. It's very hard to say what is overlapping in 3D. Okay, this is a really bad 3D latent space. Let me run once more. Maybe I have to run for a few more epochs. I don't think we have reached too much convergence. And this is still autoencoder. In variational autoencoder, let's look at fashion MNIST. We were about to see that. Okay, so this is the fashion MNIST for the variational autoencoder. We just coded from scratch. I showed you this is with latent dimension 128. Previous one was 64. And reconstructions are fairly good. But you see these patterns on the t-shirt, on the jacket, it's gone. It's not there. Then these are the reconstructions from random latent vectors. So truly, variational autoencoders are actual deep generative models because these are now generative AI images. Although it is the most primitive, the kind of generative AI images you can construct these days are amazing. But technically, from a fundamental standpoint, these images are generative AI images, which we generate from pure numbers. Numbers are converted into these images. We can do the same thing for color and higher dimensional images, but in the encoder decoder will become much more complex if you really want more expressivity, and latent space will be more having more dimensionality. Plus, you will have to run for more epochs, so computational cost will increase. But this is something that is truly demonstrative, and you can see the power of variational autoencoder compared to autoencoder themselves. Autoencoder could not have such a high reconstruction power, but variational autoencoders, because it captures the latent variables with as a probability distribution, it has much higher power to learn and generalize. That's the difference. So I think this is a good time to stop the lecture. I will post an assignment where I will ask you to plot the latent dimension in 2D, 3D, and more dimensions using principal component analysis for MNIST as well as for fashion MNIST. That is one thing. If there are any other data set like CIFAR 10 or some grayscale data set that you want to use, feel free to use that and see how the reconstruction looks. Why autoencoder is used instead of CNN? It's not instead of CNN, right? CNN is basically a convolutional neural network at the end of which you can do image segmentation, you can do classification, you can do detection. It's not instead. Autoencoder is a deep generative model. CNN is not typically used for generation. That's the main difference. CNN is used within generative models, but the usual CNNs like ResNet, it's not used for generation. It's used for image understanding and then for making some predictions on top of it. Here, it's neither for classification, nor for detection, nor for segmentation. This is a deep generative model. So this understanding will help you a lot in understanding diffusion model. That is where we want to go next. So in the next lecture, we'll be discussing about diffusion. And how many of you have heard of LLMs, diffusion-based LLMs? Have you heard of that? You might have seen videos, GIF images in LinkedIn and all, which were the entire output of LLM is not coming token after token, but the entire context window, whatever is the context window length, that much is displayed all at once. Text. Usually in LLMs, text is displayed token after token. But in diffusion model, you produce the entire output at once. So in LLMs also, in text-based generation also, same idea is possible. So just have a look at that. I think Dr. Raj is releasing a series also about diffusion-based LLMs. So just check it out. But the same idea of latent space and embedding items in a latent space and then producing it, not using variational autoencoder, it's using diffusion models, which we are yet to discuss. But the same idea will apply there. So I think if you understand VAE in depth, it will help you a long way in understanding many other things, especially in generative AI space. So thank you so much. I'll be posting one assignment based on VAE. For autoencoder, there is no assignment, but just for VAE. So just try to solve it. So next lecture will most likely be the last lecture for diffusion model. So we'll try to coding a diffusion model from scratch. I have to figure out how to make it simplified, but we can do something about diffusion models. And about Dino V1, I will record a video a bit later and I'll post it so that you can go through the video and notes and code in a self-paced mode. So this bootcamp is coming pretty much to an end. So next week will be the last lecture for the series. Then one model which I deliberately omitted is the mask2 former. So mask2 former I had discussed in the beginning, but the reason why I omitted is because we had discussed SAM, and mask2 former is basically completely obsolete in my opinion if SAM is around. So since we discussed SAM, I thought there is no point in discussing mask2 former. And the SAM paper is anyway much more popular. So far the topics that we have discussed are, we have discussed generative model briefly. We are just starting it. We have to discuss diffusion also. Before that, we discussed about VLM. In one of the earlier lectures, we had discussed about coding nano VLM. In between, we discussed transformers for detection, transformer for segmentation, and transformer for classification. And before all of that, we started with the transformer architecture itself, self-attention, then modified simplified self-attention with no masking, self-attention with masking, then multi-head attention, etc. So the path that we have taken to reach till this point is very long and it's very fascinating. So diffusion model technically will require two classes, but what I'm planning to do is, so there are two things to discuss. One is the original diffusion model itself, which was proposed in 2020, I think, the DDPM paper. The second one is stable diffusion. So stable diffusion is of course much complex. So for stable diffusion, most likely I will do a paper dissection video and I'll post it separately. But in the next lecture, I don't plan to cover stable diffusion in detail. I will, however, cover DDPM. So with that, we will wind up the series. But this has been too long. I expected it to wind up somewhere in the beginning of January or something, but the number of lectures went longer than I expected. So GAN, I have actually made an entire video on GAN. I think it was I had an explainable AI series. I think in that I have made one entire video on coding GAN. So GAN produces more, there is no probabilistic space or anything. GAN produces very sharp images. It's really good if you want to truly generate images belonging to one specific class. Let me show you one website. Actually, you might have seen this already. This person does not exist.com. So these are images produced using GAN. I don't know which GAN model, one of them. And each time you refresh this image, this is not even, the latest generative AI model. This model was proposed many years back, I think. And look at these images. These are all human faces, but these are all fake people. These are all AI generated images. And look at the kind of, how sharp it is. It's not blurred. It's very sharp. It's impossible to say it's AI generated, but it's completely AI generated. And this model, this GAN, the original vanilla GAN model came much before. So I'll find a video link and I'll post it in the Discord channel. But all right, everyone, thank you so much. Please attempt the assignment. I want to do one kind of a big project. I want to propose a big project, but for that, I have to make sure that most of you have submitted your assignment. Right now, I think most of you have not submitted the assignments. I can only see some names, common names who constantly submit assignments. So if you do submit all the assignments, I can post a difficult project for you to attempt. All right. Thank you so much. See you again next week. It's been great. I hope you are enjoying the series. I know that many of you are yet to catch up on some of the last few lectures videos, but do catch up. I think you will learn a lot. Thank you so much. See you once more next week.